My name is Adel Javanmard from University of Southern California, and today I'm going to talk about precise trade-off in adversarial training for linear regression. This is joint work with Mahdi Soltanolkotabi from USC and Hassani from University of Pennsylvania. Okay, let's dive in. As we move towards deploying modern machine learning systems in domains such as autonomous vehicles, in robotics, in medical diagnostics, it's important to note that many of these application domains are safety critical in the sense that recommendation, detections, and decisions that machine learning systems make would impact directly people's lives. And that said, it's super crucial that these learning models are robust and trustworthy. However, it's now very well known that modern learning systems are very fragile to specific variation in the input. Probably the most well-studied of this type of variations are small norm-bounded perturbations in the input data. And these perturbations often lead to surprising misclassification errors from the machine learning systems, although these perturbations are totally imperceptible by the human eyes. And in this regard, adversarial training techniques have been the method of choice to combat such adversarial attack. However, adversarial training often leads to significant deterioration on the clean, not corrupted test data, in the sense that there is a conflict between robust accuracy, which is how the model will perform on perturbed data, and the standard accuracy, which means how the model is performing on the non-perturbed clean data. And recent work has investigated such trade-off and observed that several key factors would impact the trade-off between the standard and robust accuracy. There are, of course, many important questions that are still open and require the fundamental understanding of this trade-off. And the goal of this talk is to focus on linear regression, which is a simple yet very foundational learning setting. And we would like to answer some important questions like what's the fundamental trade-off between standard and robust accuracy in both finite and infinite data limit? Can we achieve this trade-off algorithmically? And what's the role of over-parameterization and the size and quality of the training data set on these trade-offs? Okay, this is the outline of the talk. I will continue by problem formulation, and then I will go to the main result and wrap up with the proof sketch. Let's get back to the setting of the supervised learning. You have n data points, xi, yi, generated IID from some common law distribution P. Xi is the feature vector in the dimension, and yi is like the response variable or the feature or the labels on the I sample. And the goal of supervised learning is to fit a model to this data and use it for prediction. A common approach is to assume that you have access to a class of models parameterized by theta, and then you try to estimate theta by minimizing a loss over the training set. So that would be empirical loss minimization. And once you have this estimate, you can try it on a new test data point coming from the same distribution. And we call the expected error on the test data to be standard risk. In adversarial setting, the situation is quite different. You can think about it as a game between the learner and an adversary. The learner, again, has access to the uncorrupted training data. So XIY is still coming from distribution P. And the learner estimates some model theta hat. What's different is that when you are trying to test the model on a new data point X and Y, you have an adversary that will perturb your feature X to X plus delta. So you have an additive perturbation, and delta is coming from some set S, a predefined perturbation set. And notably, the adversary would choose delta after observing X. The adversarial risk would be the expected error of the model theta hat on this perturbed data point. So instead of testing it on X, you test it on X plus delta. And as I said, the goal for this talk is to understand the trade-off between adversarial risk and standard risk. We'll focus on linear regression, a very simple model where yi is linear in terms of theta 0 and also the feature vectors. We focus on xi being Gaussian from IID covariance, but you can generalize the result to non-trivial covariance matrices as well. And we focus on L2 adversarial perturbation. So the set S is given by vectors delta, whose L2 norm is bounded by some epsilon test. Epsilon test would be sort of the measure of the adversary's power. Okay, let's go to the main results. The first set of results is about the fundamental trade-off between the standard and the adversarial risk. By fundamental, I mean that we want some trade-off that holds regardless of the computational power of the learner and the amount of training data that she has access to. We want to come up with a trade-off that holds for any estimator, basically. And this brings us to the Pareto front. The idea is that for any estimator theta, you can compute the statistical risk and adversarial risk, and this gives you a point in this two-dimensional subspace. And as you change this estimator theta, you get a region in this two-dimensional space. And we are interested in characterizing the Pareto front of this region. The Pareto front are the points that you cannot improve both of these risks by moving from these points. How do we characterize this Pareto front? This boundary, this front, is basically the intersection of the region with the supporting line. So you can try to characterize this front by solving a weighted sum of the statistical risk and adversarial risk. Let's say the weight is lambda and the estimator is theta of lambda. As you change lambda, you get different points on the Pareto front. So we compute this optimization very accurately, and then we get this Pareto-optimal curve. This is the black curve. And again, I want to emphasize that this is the optimal trade-off with unlimited computational power for the learner and arbitrarily large sample size. So this is basically a trade-off that you cannot beat. The first observation is that, of course, there's a trade-off between the adversarial and statistical risk. For instance, if you want to reduce the adversarial risk, you probably would pay in the standard risk and the other way. The second question is, what's the algorithmic trade-off between these two risks? Can we get close to the fundamental trade-off by some low computational estimator and also limited amounts of training data? For this one, we need to focus on one specific class of estimators. So I will focus on this class, theta of epsilon, where epsilon is a non-negative number. And these estimators are constructing by solving a min-max optimization problem, a saddle point problem. And this estimator has been proposed in a couple of years ago. And the idea here is that although the learner has access to the clean data, it takes into account the future possible adversarial attack. And instead of just solving the empirical loss, it tries to put herself in the shoes of the adversary and mimics what the adversary will do with the test data to the training data. In other words, instead of feeding yi to xi, the learner tries to feed yi to xi plus delta I, where delta I is chosen in a worst case manner. The other interpretation is that you can think of this optimization as data augmentation. This trick would be similar to data augmentation, where instead of having just xi, yi, you enlarge your data set by xi plus delta for all possible delta with bounded norm. The other interpretation is model smoothing. You basically want to get the same label for all the points xi plus delta. And this will smooth your model, and smoothness brings robustness, which means the prediction by the model cannot be abruptly changed by small perturbations in the input. Okay. We focus on an asymptotic regime where the number of samples n is going to infinity, the number of parameters p is also going to infinity, but the ratio goes to some parameter delta. So delta is basically telling you on average how many samples you have per parameter. We also assume that the variance of the noise converges to some value sigma square, and also the second moment of the signal would concentrate on some bounded value. This is the main theorem that we have. Under this asymptotic regime, we propose a convex-convex optimization problem. The function d here has 5 arguments, and these arguments are just scalar variables. And it's a min-max optimization. We prove that it has a unique solution, and once you solve this optimization, you can characterize the statistical risk and adversarial risk in terms of the solution of this optimization. Again, all of the variables here in the first optimization are scalar, so that would be a low-dimensional, basically 5-variable optimization problem, and you can solve it very fast and accurately. And once you have it, you can characterize precisely what would be the behavior of these two types of risks. What's the expression for D? This is the exact expression for the function D. It's quite involved. Later, I will explain how you can drive this expression for the function D. Okay, once you have this precise characterization of the two estimators, we can try to draw the trade-off between standard risk and adversarial risk. As we see, when delta grows, the algorithmic trade-off achieved by this class of estimator would converge to the optimal trade-off, the black curve that we have. And the second thing is that there is a very good consistency between the simulation and the theoretical curves that we have. Armed with such precise characterization for the standard and adversarial risk, we can also capture the effect of different factors on this trade-off. Here, I'm plotting the standard risk versus epsilon, the adversary power. And as we see, for small to moderate epsilon, there is a decline in the risk in the standard risk. In other words, for these values of epsilon, adversarial training also improves the standard accuracy. These are for delta less than 1, so this is for over-parameterization, but you have the same behavior for delta bigger than 1. This is where you have more samples rather than the parameters. In the next set of plots, I'm drawing the standard risk versus 1 over delta, which is P over N. When epsilon is 0, this is basically the double descent, the classical double descent that have been observed. And when epsilon is non-zero, we basically see something similar to double descent, but in an adversarial training model. The interesting point here is that the interpolation threshold, as well as the magnitude of the overshoot of the risk at the interpolation, would change with epsilon. It depends on the adversary power. And again, you can exactly characterize how the location of the interpolation threshold and also the maximum risk would vary with epsilon. Okay, let's go to the proof sketch. The main theorem that we had was this one. Again, to remind you, there was a low-dimensional optimization problem whose solution would completely characterize the standard risk and adversarial risk. So the main question is how to drive function D. I've split the proof into 3 steps. The first step is simplification of the min-max loss. This was the estimator that we start with, theta of epsilon, that was given by saddle point estimator. And the first step is that the inner maximization here can be simplified in a closed form. You basically get this expression, and then your estimator would be just a minimizer of this expression. You can see that this is sort of a regularization by L2 norm of theta, but this is not an additive regularization. The regularization is indeed in the argument of the loss. Okay. Now, once you have this simplification, I just introduce a new variable vi, which is the residual or the error on the sample I, and then I add this definition as a constraint to the optimization. So this is just a change of variable. Now, if you take the dual of this optimization, it has a form as follows. It has a form of a minimax optimization in terms of 2 vectors u and z. The first term is bilinear in u and z. It's u transpose xz, plus a function psi, which is convex in z and concave in u. And we call it a primary optimization. Now, we want to understand what the asymptotic behavior of the solution of this optimization problem is. And for that one, we use something called convex Gaussian min-max framework. This has been developed by this research group to characterize the asymptotic behavior of M estimator in a non-adversarial setting. We extend this framework for the adversarial setting. And the main theorem is that if you have a function phi of x of this form, in a proper sense, it will be approximated by something called an auxiliary optimization, where the matrix X would be replaced by 2 vectors G and H. So instead of dealing with Gaussian matrices, you have Gaussian vectors. And instead of working with the primary optimization PO, you need to work with the AO optimization. One thing that I would like to note is that the classical CGMT framework for the non-adversarial setting will not directly apply to our setting. And we had to come up with intricate derivation and novelty to extend the application of CGMT. Once you have this AO optimization, we want to see what's the asymptotic behavior of this one. So we take the limit of the objective, the pointwise limit. This gives us the function D. But we've proved that the convergence is just not just pointwise, it's indeed a uniform convergence. So the solutions of the AO problem would also converge to the solution of this optimization problem here. Some remarks: D, again, is a function that's convex in the variables that we are minimizing over, and it's concave on the variables that we are maximizing over. It's a low-dimensional optimization problem in terms of 5 variables, so it can be solved very fast, very accurately by gradient descent. It has a unique solution, and once you have the solution, you can characterize a statistical risk and, standard risk and adversarial risk in terms of its solution. With that one, I would like to wrap up the talk, and thanks for your attention.